So we talked about the natural numbers, we talked about the integers, we talked about variations of those. We now talked about the rational numbers being countably infinite, being the same cardinality as the natural numbers. And we also saw algebraics, that if we add in a whole bunch more, we still get the same cardinality as the natural numbers. So let's now jump up to maybe the next largest set of numbers that you're used to working with, and that's the set of all real numbers. Everything between negative infinity to infinity. Is this going to be countably infinite or uncountable? So the theorem that we'd like to show is that R is uncountable. So we would like to somehow prove that the set of all real numbers cannot be listed. Because we said if we can form a list, has the same cardinality as the natural numbers. If there's not a list that works, well then it's not going to be countable. So, and because we know that this is going to be infinite because the natural numbers is contained inside of this, it's going to be infinite. So if it's infinite, it's either going to be either countably infinite or uncountable. So this is indeed uncountable. So the type of proof that we're going to use is we're going to use what's called Cantor's diagonalization. So Cantor was a mathematician, I believe, in the 1800s, and he was all about trying to understand these different things of infinity. He had a whole lot of understanding of different sets and trying to work with these. And there was a whole lot of people hating on him because he was like, wait a minute, guys, I think there's uncountable sets. And people are like, no, we will kill you. Shut up. But he still was like, wait a minute, I actually think there is this. So we're going to work through his proof. I don't think he got killed by people, but I think he died some other way. Obviously, he's dead. He's from the 1800s. But nonetheless, Cantor's diagonalization argument, we're going to see how can that prove that the set of all real numbers is uncountable. So what this looks like is it's going to be a proof by contradiction. So we can now suppose that the real numbers is countable or countably infinite. We know it's not finite, so okay, so suppose that it is. What that means is that we can form a list. So I'm going to form some type of list. So for each of these, I'm going to use some subscript notations to indicate each location. So I'm going to form a list of all of the real numbers. So the first one I'll form would be, say, a sub 1, 1, dot, a sub 1, 2, a sub 1, 3, a sub 1, 4, and so on. The next one would be a sub 2, 1, dot, this is like the decimal point. A sub 2, 2, a sub 2, 3, a sub 2, 4, and then the next one would be, say, a sub 3, 1, dot, a sub 3, 2, a sub 3, 3, a sub 3, 4, and then the next one, a sub 4, 1. You get the gist here of what's going on, is that I'm taking at least some subset of these, and I'm going to form a list. There's obviously an infinite number of these, and for all of these, if I include a number that ends, I just keep adding zeros to the very end of it. So I can add an infinite number of zeros and it's still the same. So hypothetically speaking, let's say this is my list. Then, if I can list all of the real numbers this way, every single one of them, I'd like to take a look at a very special number. I'd like to take a look at a number that's formed by taking this first number. I'm going to take this number and I'm going to change it. I'm going to add 1 to this. If it's 9, I'm going to go down to 0. Okay, but I'm just going to add 1 to basically make it different than this. So let's say, for instance, this was the number 2.3974, blah, blah, blah. The number I'd like to take a look at, the first digit is going to be 3. Then the next, in this one, to continue forming this number that I'm looking at to figure out where it's in the list, I'm going to take a look at the second number in my list, and I'm going to pick this number, but I'm going to add 1 to it. So let's say this number here was 4.932, blah, blah, blah. I'm going to add 1 to it, so my next digit would be 0. I'm going to go to the third number on my list and say, this new number, I'm going to take this third digit, and I'm going to add 1 to it again. So I don't know, whatever this would be. Let's say, for instance, this was, say, 5.73, blah, blah. This second one after the decimal, I'm going to add 1 to it, so I'm going to have 4. And I'm going to keep doing that for all of these numbers. So I have a list of all the real numbers. I'm looking for this number that I'm formed by taking each of these along the diagonal, and I'm going to form the number where this is the first, but I add 1 to it. This is the second digit, but I add 1 to it, and so on and so forth. This number that I found, is this a real number? Well, yes, it's a real number, right? I have a number, and then I have a whole bunch of other numbers, and this is just a real number, right? There's no imaginary parts. But is this the first number on the list? Well, no, it's not the first number on the list because it has a different first digit. Is it the second number on the list? Well, no, it's not because it has a different second digit. Is it the third? No, it has a different third digit. Fourth number? No. So every single number on this list, it's going to differ in at least one location from the number that I picked. So what I have now is I have a real number that is not the same as any of them in this list. And that goes on forever. But how can I have a real number that's not on the list if I said that I could list every single real number? And so that's the contradiction. So what we see is that this number we formed is not in the list. It is not on the list. It's nowhere. It's different than every single one. So what this means is I have a contradiction. I do not have a list of every single one because there's one that's not in the list. So this is a contradiction. So what that means is that R cannot be listed. R is not countably infinite, but since it is finite, it is going to be uncountable. So this says that R is uncountable. Now, this is a slight twist on the way that Cantor proved it. You could go ahead and research him if you want. A very fascinating man. He was a very strong Christian as well. There was a lot of people from the church who were like, no, listen, you're an idiot. You're not supposed to be doing this. This is going to try to disprove God in some manner. God's the only thing that's infinite. You can't prove that something else. These sets are infinite. And he's like, wait, but I think that they are infinite. And he was right. Other people were stupid, but nonetheless, you can read about him, and Cantor was a very fascinating man, and he came up with this really important result, or helped us come up with this really important result, that the set of all real numbers is uncountable.